To look at some of the major approximation methods we use for time-independent problems in quantum mechanics, we're going to use an example problem. Specifically, we're going to look at an electron inside a potential well with infinitely high barriers as usual, but with an applied electric field. This problem is complicated enough to show what happens with various different models, but simple enough that we can conveniently work with it. It's also a problem that has exact analytic solutions, even if they are slightly obscure, so we can, if we want, compare with an exact answer. Incidentally, this particular problem turns out to be of substantial practical interest. It's at the core of devices called quantum well electroabsorption modulators. These are devices made from layered semiconductor structures containing individual layers of about 10 nanometers thickness. When we apply a voltage to these structures, we can shift the quantum mechanical levels around and significantly change how much light the structure will absorb at a given light wavelength or frequency. Such devices are actually one of the major ways that we impose signals on the light beams we use for all of our internet connections over optical fibers. Before trying out our various methods then, we need to set up this particular problem in a convenient form, so we'll start by doing that next.
So we're going to consider an electron in a potential well with infinitely high walls as usual. It will have a thickness, Lz, and the usual notation we have for the energy of the first confined state in that well would be E1 infinity, the infinity indicating we've got infinitely high walls as usual. We'll be using that as an energy unit later on, and we'll be using this thickness as a distance unit later on. And then we're going to apply an electric field to it. We're going to put a field on that is pointing in this direction with a magnitude capital E. And that will give a change in potential energy from one side to the other of the well of little e, the electronic charge, the magnitude of it, times the value of the field, times the thickness, Lz. So as we go from one side of this well to another, an electron would have an energy that increased by this amount. So, formally, the energy of an electron in an electric field, capital E here, simply increases linearly with distance. A positive electric field in the positive z direction pushes the electron in the negative z direction. It's pushing it downhill in the negative z direction with a force of magnitude, the electronic charge, times the magnitude of the field. So the potential energy of an electron in a field pointing in the positive z direction is one that increases in the positive z direction because the force is trying to push it in the other direction. And the form of this potential energy as a function of position z is the electronic charge times the field, that's the force, times the distance, that's z. Now, in this problem, we're going to choose the potential to be 0 in the middle of the well. Hence, within the well, the potential energy is little e, the electronic charge, times the magnitude of the field, times the position relative to the center of the well, so that when z is equal to Lz over 2, that is, in the middle of the well, the potential energy would be 0. That's just a convenient choice for us. It doesn't actually matter what we choose, but we'll choose this one for convenience. So the Hamiltonian becomes, as usual, our kinetic energy term here for this one-dimensional problem, and then here explicitly is our potential energy term. We can usefully set this problem up in dimensionless units. A convenient unit of energy is, rather obviously, the energy of the confinement of the first state in the original infinitely deep well, so E1 infinity. And in those units, the eigenenergy of the nth state of the problem will be eta n in dimensionless form. That's the actual energy of the nth state in our real problem, including the field, divided by E1 infinity, our unit of energy. A convenient unit of field to use here, some field E naught, is one that would give one energy unit of potential change from one side of the well to the other. So that would be a field unit that corresponds to that confinement energy of the first level in the well divided by the electronic charge E times the width of the well, Lz. So the dimensionless field then will be some number f, which is the actual field divided by this field unit here. And obviously a convenient distance unit in this problem is the thickness, Lz, of the well. So the dimensionless distance will be Xc here, which is z over Lz. From the original Hamiltonian, which we wrote out in this form, dividing by this energy unit, E1 infinity, and using dimensionless units gives this form of the Hamiltonian, now a dimensionless form, 1 over pi squared d2 by dxc squared plus f times xc minus a half here. And the time-independent Schrödinger equation in these dimensionless units would simply be h operating on phi of xc is equal to eta, our eigenenergy we hope to calculate, times phi of xc. For the unperturbed problem, that is the one before we apply the field to it, we can write this so-called unperturbed Hamiltonian within the well then as the usual simple Hamiltonian with a potential of 0. There's no potential energy out here. We've chosen it to be 0 in the unperturbed situation when we're within the well. And we know the solutions to this problem, and writing them in this normalized form, we would have our corresponding Schrödinger equation with the unperturbed energies written as epsilon n, and then the wave functions of this unperturbed problem in these dimensionless units would simply be psi n of xc equals root 2 times sine of n pi xc. So just a dimensionless form of the usual solutions of the infinitely deep well problem.